In this video, we're going to explore a topic that straddles formal logic and digital design. Namely, which Boolean operators / digital gates are really necessary. Instead of the multitude of possible operators, can we get by with only a few or even one? Within propositional logic, there are a number of common operators, such as and, or, not, XOR, implies, etc. These are often called truth functions or logical connectives. They take as input Boolean values, true or false, and return a Boolean value. For example, the two-input AND operator returns true if and only if both inputs are true. Propositional expressions are constructed from the two Boolean constants, true and false, variables, and the connectives following certain syntactic rules. Truth functions are total functions. That is, for every possible combination of Boolean inputs, the function returns a unique output. And since all inputs have only two possible values, a truth function with k inputs can be described completely by specifying the output for each of the 2 to the k possible input combinations. Because of these constraints, a popular way to represent a truth function is using a truth table. For every possible combination of Boolean inputs, the table shows the result of applying the function to those values. It's pretty easy to see that any truth function is defined completely by the corresponding truth table. Shown here, for example, is the truth table for the two-input AND function. We've named the parameters x and y, but the names are arbitrary. Let's consider a slightly more complex function. Here's the truth table for a three-input truth function we'll call C. From any given truth table, we can derive an equivalent propositional formula by following a simple process. Let's illustrate this with our function C. By examining the truth table, we see that there are exactly 3 combinations of inputs for which C returns true, corresponding to the 3 rows of the table with T in the final column. We've labeled these as case 1, case 2, and case 3. The first such row is case 1, where x, y, and z are all false. As a logical formula, this row can be characterized by the propositional expression shown here, since all of the input variables are false for this case. The next row for which C returns true is case 2, the row in which x and z are false and y is true. This yields the formula shown here. The final row for which C returns true is case 3. In this row, x and z are true and y is false. This yields this formula. Now notice that C returns true only in these 3 cases. That is, C returns true if case 1 holds, or case 2 holds, or case 3 holds. Logically, that corresponds to the formula shown here. And this, in turn, expands to the formula shown here. Hence, this formula is just another way of describing precisely the same truth function as our original truth table. It's pretty easy to see that one could generalize this process to take any truth table and generate a logical formula that describes the same truth function. The number of inputs wouldn't matter. But by construction, this process always yields a logical expression that only uses the connectives and, or, and not. So what we've shown is that any truth function can be characterized by a truth table, and that any truth table can be characterized by a logical formula using only the input variables and the logical operators and, or, and not. The upshot is that the operators and, or, and not are sufficient to define any possible truth function. In turn, that means that for any propositional expression, there's a logically equivalent expression using only and, or, and not, since any propositional expression can be considered a truth function of its variables. We say then that the set containing and, or, and not is functionally complete, meaning that this set is adequate to define any truth function. Sometimes we'll just say that the set is complete if the context is clear. It's natural to ask whether there are other sets of logical operators that are also functionally complete. For example, could we get by with fewer than 3 operators? The answer in both cases is yes. You may recall from your logic class that OR can be defined in terms of and not, as shown here. This means that any occurrence of OR in a formula can be eliminated by replacing it with a corresponding instance of the expression on the right-hand side of this equivalence. And since we've shown that the set containing and, or, and not is functionally complete, it follows that the set containing only and not is also functionally complete. OR is redundant. We could similarly eliminate and in favor of or and not, using the equivalence shown here. Thus, the set containing or and not is also functionally complete. There are 2 operators that are individually functionally complete, NAND and NOR. To be more precise, it's the sets containing only NAND or only NOR that are functionally complete, but you know what we mean. NAND, short for not and, is sometimes denoted in logic by the upward arrow. It has the truth table shown here. We can show that NAND alone is functionally complete by showing how to convert all of the elements of any other complete set into equivalent expressions using only NAND. Consider the set containing and not. The 2 formulas shown here show logically equivalent forms using only NAND. We'll leave it to the viewer to verify these equivalences using truth tables. NOR, short for not or, is sometimes denoted in logic by the downward arrow. It has the truth table shown here. We can show that NOR is functionally complete just as we did for NAND by showing that it's adequate to define and not. We'll leave that as an exercise for the viewer. Notice that any superset of a complete set of operators is also complete. Not every set of operators is complete. For example, consider the set containing only and or. Both of these operators have the property that, given only true inputs, they return true outputs. It's easy to see that this property holds for any arbitrary expression created using only and or. It's not too hard to prove this by induction on the number of operators in the expression. Now, suppose that you tried to define the operator not using only and or. The truth table for not is shown here. Implementing not requires generating a false output from a true input, something that is impossible using only and or. That means that there is at least one truth function, namely not, that cannot be defined from and or. Hence, the set containing only and or is not functionally complete. By the way, it's often more difficult to prove that a set is not functionally complete than to prove that one is. In the 1930s, Claude Shannon showed that Boolean logic was a convenient way to describe combinational circuits. Corresponding to each of our logical operators is a gate in digital logic. For example, shown here are the symbols for the gates corresponding to AND, OR, NAND, NOR, NOT, and XOR. Each of these symbols denotes a physical device that computes the corresponding truth function. An AND gate, for example, behaves as follows. We place voltages on the input wires representing Boolean values. After a short delay, the device produces a voltage on the output line representing the Boolean value that is the logical AND of the inputs. The other gates work analogously. What we've said about complete sets of logical operators applies equally to collections of gates. For example, we showed that NAND is a functionally complete operator. Therefore, the NAND gate is also functionally complete. That means that any combinational circuit whatsoever can be constructed using only NAND gates. Here, for example, are 2 circuits constructing NOT and AND using only NAND gates. Compare these to the logical equivalences we showed earlier, demonstrating that NOT and AND can be defined using NAND. You'll see that our gate diagrams express precisely the same information, but in the context of gates.